I think it is better to open up a KMS site.
Sorry, what is it?
KMS에 박스 열어가 이제 제출하는 것이 더 저는 편이지.
Either way, that's okay. So long as I have access to that, I'm happy.
힘들다면 저만 올리겠습니다.
Good. So long as I can see the report, I'm happy. Any questions so far? Okay, so good. So we are discussing renormalization. We are almost there. Okay. So far, we talked about vacuum polarization. Then we talked about vertex normalization. And so far for these two, the way we have renormalized the UV divergences that we encountered by actually doing the computation. So this, as the name suggests, okay, so we named it called vacuum polarization. But we could have called it photon self-energy. Here, we used to call it a electromagnetic dipole moment. And I explained why this is related to a magnetic dipole moment, in particular G minus Q. But I could have called it, which I called it vertex diagram or vertex renormalization. So these two different, if you like, name scheme. Obviously, physics name scheme is not what's really important. Which really, the physics is what's important. It is the following. So far, I have discussed renormalizing the UV divergences in these diagrams in terms of, this vacuum polarization, which means that there was associated observable, but actually measuring the potential, Coulomb potential. And here, obviously, there is this observable we talked about. So, in a sense, so far we normalize using, as you talked about many times, either on shell or physical perturbation theory sets. Okay? And at the very beginning, when we talked about the 5 to the cube theory, and then we also encountered UV divergences, we said that we can think of renormalization either in terms of on shell or physical perturbation theory, or we can actually think this in terms of renormalized perturbation. Okay, so either should work out. Now, in principle, I mean, so what was the difference? Just to quickly remind you, here we said that there's a pair of parameters. Like, for instance, electric charge. So let me just put B to say that it is bare parameter. And then these bare parameters has UV sensitivity already in such a way that if you compute the loop corrections, right, then you should automatically get the final answer in such a way that this UV sensitivity part should be arranged so that you get the final answer, right? So that's how we talked about it. And discussing renormalization in the language of on-shell or physical perturbation theory is clear and nice, but sometimes it is hard to use this scheme because what if there's a diagram? So now we're going to talk about this diagram, right? So now we talk about the electron self-energy as opposed to being a photon self-energy. Sometimes you can draw a diagram or you can have associated Green's function. For instance, this will be associated with time-ordered super function of electron. Okay. So the point is that in some cases, certainly you can draw a diagram as a Feynman diagram says, and there's certainly associated, time-ordered vacuum expectation value, but you may not be able to identify clear and well-defined observable on-shell or physical observable associated with those diagrams. Nevertheless, if you compute this diagram, you will see the divergences. You can ask yourself that, how should I deal with those UV divergences when you cannot actually see or define good notion of observable associated with those diagrams. Okay? So nevertheless, we should be able to make sense of these diagrams, and we should be able to remove UV divergences. And in that sense, in that context, this approach is slightly more convenient. Okay, so what was the difference here? Here, basically the difference was that bare parameter, which had a UV sensitivity. Now we view this as renormalized, parameter. In this case, calculus that I'm talking about, which is UV finite. And then there is a countant term piece. Okay, so here we take the active, viewpoint that we're going to add, as I will discuss in detail, we're going to add the UV sensitive. So now this will be UV sensitive. So we're going to design or add a counter terms, local counter terms, which does include UV sensitivity in such a way that if you compute the loop diagram in terms of renormalized parameters, which are finite. So in these cases, you only get explicit or manifest UV divergences that comes from the loop itself, okay? And then you compensate those by adding contribution from the counter, as you will see today. So that's the slight difference, but also I will try to establish the equivalence between these two approaches today. Anyway, so that for the last renormalization of QED that we talked about, the electron self-energy, we're going to take this most, okay? So this is just to tell you that you don't completely lost. Okay, so let's talk about that. So we want to compute this. So and then today, just to simplify, I'm just gonna write like this. Okay, without even writing down any argument, no vacuum, no T, anything. Okay. So then in momentum, so this is like position space, and then I can do the Fourier transform to rewrite this in terms of momentum space Green's function or 2-point function. I times. So therefore, either I write this way, or if I specify B, what I mean by that is I mean momentum space 2-point function. So in general, in fully general sense, this will be represented by this block. Okay, but in detail, this will have a tree level is that you will have some contributions, loop contributions. In this case, we are talking about this, and there can be I put computation by accident, and there can be many other loop diagrams in principle we can draw. Okay, so we are going to compute this. Well, as by now you understand, I'm going to write down the amplitude, and then you will finish the computation. But at least we will look at the computational part later. But let's first understand conceptually what's really going on and how we have to organize in order to understand the renormalization of this thing. Because this thing has more than one renormalization that we have to understand. So before we actually compute this thing, we're going to first talk about the big picture. So if you lose the way, even if you can compute this thing, you may not be successful. But if you actually understand the big picture, you may struggle a little bit about the computation, but you're not going to lose the way. You know how to think about this. Okay, so let's first talk about the big picture, the vector part. Okay, so first of all, let's look at this very roughly. So this thing, now I'm just going to do very roughly. Two vectors of coupling, and then loop momenta, let's use K because we've been using K. And then there's a one photon propagator, so that will give me like 1 over K squared. And then there's a one fermion propagator, and then that will give me 1 over K or K slash. So I'm being super naive here. Okay. But if you do a little bit more carefully, so naively then, if you just look at this and then try to see superficial degree of the divergence, there's a fourth power in the numerator, and there's a third power in the cubic power in the denominator. You might say this must be linearly divergent. Okay, but even without a fancy thing, if you actually write down carefully this amplitude, you should get that something that looks like minus E squared. Again, I'm not being completely careful about everything, every stuff. So eventually, what you're gonna get. I'm sorry, putting something. So P slash something to M X. At the end, the point is you should get this. So you might say, okay, I get a 4 powers of K, which is there. And then effectively, I must have only 3 powers in the denominator. That is true because this is 4th power in the K. What I'm saying is that one vector of 1 power of a dimension full thing is only made of this finite UV insensitive parameters, IR parameters. Okay. In fact, if you actually go through calculation, this one actually included extra pieces of K slash bits. Then you might say, okay, now there's actually 4 power, another power divided by subtracting 4. This is actually linearly divergent. But as we talked about, this entire integral is a function only of K squared. This is linear, and we talked about the fact that it should not make any contribution. Okay, so therefore linear piece actually does not appear. And then the remaining piece, as you now see it here, is that this should be logarithmically divergent. Okay, so let's first understand the big picture again. So what? Okay. So then we have discussed this technique that I presented a while ago. So now if I call this to be amputated to by I sigma 2 P slash. This is a function of external momenta P, and then this is my notation for this particular amplitude. And then we just have identified the fact that this is a logarithmically divergent. Which means that if you recall, if I do make a derivative in terms of external momentum once, this object, sigma 2, this must be UV finite. Okay? We talked about if somebody gives me arbitrary UV sensitive thing, if I take enough, number of a derivative with respect to external momentum, you should get the final answer. In this case, this was a logarithmic, so one single derivative is sufficient to bring it down to UV finite answer. All right, so then let's integrate back. That means that even without even computing this, we can already sort of anticipate the formal structure of this object. So first of all, you're going to have integration constant part. Okay, so then it can be organized as A plus B slash. So remember, this is in principle function of a P slash. And then this thing should be Lorentz scalar. So I can write down, I can anticipate or I can guess the form of an integrated constant in this form. And then I will have a basically integrating back of that piece, which was UV finite. And then from now on, let me just call this to be sigma 2 tilde, which again, we call this is UV finite piece. Okay, so let's recall. So first of all, these A and B pieces, which are integration constants, they are UV divergent in general. Okay, so unless there's a magic or secret hidden symmetry. However, as we talked about, they are polynomials in external momentum and coupling constant for this particular external momentum. So this says that there's in position space says there's a local UV divergence, okay, which take this structure. Okay, so this space, on the other hand, this is UV insensitive, or you may call it UV finite. But this is in general not analytic function in general. function of momentum. Okay, so that we can say already without doing any single computation. Okay, now let's organize it, things. So what we are talking about, we're talking about IGB, which is a general two-point function, which is again represented as above. Okay, so this will look like, tree level, this, and then keep having, extra factors. Okay, so general way of organizing this thing, therefore, is that, this plot may include a lot of loop corrections, right? So for instance, as we talked about, you can add this, but you can also have a tool of corrections. Yes, this is tool of corrections, and you can keep going. Okay, you can have extra corrections and so on and so forth. There can be many other diagrams as well. So in general, this sort of diagram where I don't include external lag, and in particular, the diagram cannot be divided into two pieces by cutting one of the internal line. Those diagrams called one particle irreducible diagrams. So one particle irreducible diagram. So by cutting one internal line particle line, this diagram cannot be reduced into a separate pieces. So these are 1PI diagrams. So the generic structure, even though we are talking about vulnerable normalization, generic structure is going to be tree-level diagram, and then you're going to have a bunch of 1PI diagrams. Then you can have a resummation of the 1PI diagrams we talked about, or you will see that again. So on and so forth. And the motivation for doing this general resummation was, let's just write that down. So the tree level P slash minus M. Okay, let me not include I description for now. So then this first bit has first of all P slash minus M. So that's this external lag propagator. And then I said that let me call intermediate, this 1PI piece to be I times sigma 2, as I did there. And then there's another propagator the other side of it. And then you can keep having it. So basically, compared to this piece, the leading piece has just basically one, then sub-leading piece starting having this combination. So you anticipate that, here, what appearing here is sigma 2 I square the final powers. So the problem of doing naive perturbation theory by adding this way of correcting the leading order propagator is, once again, there's a parametric suppression versus kinematic enhancement, right? So you can be in the kinematic regime where this is not small at all compared to 1. Okay, so you fail. So naively perturbation theory breaks down, you have to resum. So if you do it, what you get is now P slash minus M. This is 1 over 1 minus X, where this is X. Is 1 minus, and then you have I that's plus, so sigma 2 M. Okay, so this becomes P slash minus M plus sigma 2. Okay, so this is resum the propagator. All right, now through this analysis, we already sort of figured out at least formal structure of this sigma 2 pieces. Okay, it has two UV divergent coefficient, especially with this structure. One is independent of momenta, the other is proportional to P slash. There's the UV finite piece. So let's plug that in. So let's keep writing. So that will look like P slash minus M, then A plus P slash, and then this, and the last one is UV finite. Okay. So now you see a chance to organize these things. This thing is proportional to P slash, so you can combine that to be like so. Okay? And then you see this, so M minus A, and then there's a sigma 2 such. And you want to see an expression that is, that has a 1 in front of p slash, so which you can achieve by dividing by 1 plus b. You get this. Okay. Now, let's do the power counting a little bit here. So let's erase this part first. Okay, so recall, without an issue of UV divergence, which we'll spend a lot of time talking about anyway, without setting aside the issue of UV divergence, these things A and B sigma 2 tilde, which all came from a single object, which we call sigma 2, computed at one loop, should be of the order of E squared over 625, right? So that's the side of it. Again, setting aside the issue of UV divergences, it should be of the order of that. Which means that this, there should be good notion of a perturbation in the sense that this should be treated as small compared to say 1 or n. Okay? So what it means is that I can, expand this in a perturbative sense. So I can first write it as I times 1 minus b. I just expand this naively. This b is very small compared to 1. And then I have b slash. And you can also expand this, which is m minus a. This may not be complete yet. We have to do it again. And then sigma 2 tilde. So let's redo it. So m minus a from b times m. So I just dropped the high order term. For instance, here, A times B corresponds to next leading order. Okay, so this is the square of this piece. So I dropped it. Here too, if I expand it here, in principle, you might say there is a minus B times that thing, which is again square of this order. So I'm dropping it. Because the precision of our calculation, we can only trust quantities which is of the order of this or bigger, right? You are not supposed to trust any quantity which is much suppressed compared to this. Because otherwise we have to include a computation of this thing. Okay? So this is the expression. Okay, now, so then I'm gonna just call entire combination this to be M renormalized. And then I also will call this numerator piece to be that too, bless you. So we have, in the end, have roughly the structure IV2 divided by P slash minus M renormalized plus. Okay. Without even doing any single calculation, we should know it should come out to be of this form. Okay. Now I'm going to say a lot of things for now. But any questions so far? Yes, that's
중간에 붙인 것 같은데 1PI를 시그마 2로 나타내는 게 그냥
yes.
이 부분까지 그래요.
Yes, this is my 1PI. Okay. Any other question? All right. Any other question? Okay. Yes. Yes. Yes, good. So sigma 2, I sigma 2 was this complication. Okay, so there's a one loop and then two coupling constant. So it goes like E squared, and then there's a one loop. I told you there's a generic factors of 1 over 65 squared, all two factors of 2 or whatever. And then in principle, this can have a lot of numerical factors, but also there can be UV divergence. And then I said that let's not worry about UV divergence because we're going to have a designated discussion about that. So generically, once I successfully get rid of UV divergences, you should go with the order of this. Hence, it is a much suppressed. So that is basically the statement that this theory is a perturbative. This should be bigger than that. What did I say? Yes, I said correctly. And this should be bigger than that, and so on and so forth. Okay, so all this A, B, sigma 2, which came from the single object, they're all perturbatively small. That's why I said. Okay, good. Any other question? Yes.
You said electric charge is also renormalized.
Good. We have done it, but not completely yet. So when we talk about the vacuum polarization, correction to the photon propagator, we learned that the effect of including bubble diagram, sorry, not bubble, vacuum polarization diagram is to renormalize electric charge. Okay, but there are several diagrams that actually contribute effectively to fully renormalize electric charge, which we have not discussed yet. That will be the last discussion we will do last lecture. But suppose let me just focus on here and then pretend that this has never been renormalized.
Never
Okay.
been renormalized.
Because I'm just looking at the 2-point function of the electron here. Okay, so if you look, so then what you should expect, again, so whole point of doing this discussion is build up the intuition, right? Before jumping into the calculation. What you should expect is that, well, our Lagrangian of QED include these two terms. Well, actually not just two terms, but and then interactions, okay, and then photon propagators. But I'm just looking at the 2-point function of the electron, which means that there are two pieces that appears in the Lagrangian. Okay, so even before computing anything, if you start including the radiative corrections, loop corrections, something could happen either of these two terms. Because I'm just looking at the 2-point function of the electron. Okay, so either something has changed here, which we'll discuss soon, or something has to change here, which at least you can identify what can be changed. In this case, electron mass. Okay, so basically, I will make a connection to this to pointing out the meaning of each of these. Okay, good. But at least for now, for this discussion, we don't have to worry about like electric charge renormalization, because then you have to look at photon terms like this. But I'm just looking at the electrical function. Okay, good. Let's continue. So first of all, now I start putting subscript or superscript. So where did I start? Here. I started here. And then suppose I took a path of on-shell or physical perturbation theory way of thinking about the stages. Okay? So suppose what I mean by that. Suppose I was computing 2-point function of electron by summing this. But suppose I was doing in a bare picture way, meaning I view this as a bare field, and then this is a bare parameter which has UV sensitivity in it already. Okay, suppose I was doing this, and then in terms of that picture, meaning your parameter is not actually just a finite, but it can be actually UV divergent. And then suppose I have done this calculation. So what that means is that what's appearing here is actually a bare parameter, right? And then, so here is a bare parameter. And you see, for instance, why did I say that this can be defined as a renormalized mass? Suppose there's an experimental way of measuring this particular combination. Okay? So if there is any experimental way of observing this particular combination, obviously there's a UV sensitivity, this A and B, which came from the existence of a loop structure in the diagram. But there's also another UV sensitivity here because I'm doing the bare picture now. So they will conspire to cancel each other, and I should get the final answer, right? So that I call it renormalized. You might say, what about this piece? Well, I organize things already in such a way that this sigma 2 tilde is already UV insensitive or UV finite. So this piece overall is completely UV finite. So the only piece, so everything here is UV finite. And then this still has a UV divergence. This is UV divergence. Yes.
Manage of the why the renormalization of matrix will be finite even if it contains A and B.
Good. So what I said was this. Let me repeat that again. I said, hey, let's imagine that there is a clever experiment which can actually measure this, meaning whatever appearing in the denominator of the propagator. Suppose we have a way of measuring that, so electron mass. Okay? Then this appears like that because not only I included the tree level diagram contribution, but also loop contributions. But at the end of the day, if there's an experiment that can actually measure this thing, inverse, meaning the denominator, full denominator, whichever way I compute this blob, the experiment should just give me the final answer. So that's the idea of this on-shell physical probability theory thing. Okay, you may add a tree plus loop, whatever, all UV sensitive stuff, but the experimental measurement should just give me final answer experimentally. So that was my point. So this is UV finite, and then this looks like there's a lot of different kind of UV divergences. But the point is that if you give me specific form of UV divergence of A and B, because I'm computing up to one loop, then this parameter changes its own UV sensitivity in such a way that you always should get the final answer. That's the idea.
You said that the bare parameter and the it also have the UV sensitive part.
Absolutely. So in this picture, this thing has UV sensitivity. I'm sorry? Intrinsically. Okay, and we even know how to determine the UV sensitive structure of this thing by demanding this should be finite. Okay, we will get there soon. But yeah, anyway, another question. Good. What about this thing? First of all, this thing is called wave function renormalization vector. So, in other words, if I define my bare field, okay, to be square root of Z2 times, let me call renormalize the field, then this thing looks like basically Z2, because this was what? So this was, remember, bare, bar. Okay, so it should be equal to renormalized bar. So what it means is that if I have this rescaling of what I call the field, okay, so if I rescale what I call the field, that's the name actually renormalization came from. We just renormalize the field, then we ended up getting, so renormalized two-way function in terms of renormalize the field will be equal to I over A slash MR sigma to the as a function of length in general. So everything here is clearly UV finite. Okay, so this is just the beginning. Now, questions? Yes.
So I think that you normalize the field size R.
Yes.
Not satisfying the normalization condition of the entire commutation relation. So that means that psi R anti-commutation of psi R and psi R bar is not equal to just zero function.
Good. So
Also, I guess.
okay, so canonical commutative relation. Good. So when we impose canonical commutation relation at tree levels, where we right, so we start out with the Lagrangian and then we quantize it in a canonical sense. We impose the commutation relation in terms of tree level field, meaning the field that appears in Lagrangian. Now we start adding a we start adding a quantum corrections to that. So your concern is valid, and then I will answer that by now actually switching my discussion to renormalized perturbation theory. So this has a closer connection to how the Lagrangian changes if I start adding loop corrections, and then from there you will see why the condition may not be violated. Okay, so that's a valid question, and then I basically start discussing that. Hopefully that discussion include answer to your question. Any other question? Good. So let's summarize what just happened. Okay, there's a computation, but basically what happened is if I resolve in terms of a bare picture, let's just call it a bare picture. What happened is you get this, but by cleverly defining, UV finite renormalized mass parameter, you get this. So basically, bare two-point function is Z2 times, where this is a waveform renormalization factor, renormalized two-point function, where everything is finite. Now, okay. Oh, good. Is it too late? No, I'm not too late. Good. So I was gonna say another thing. So if you compute this, therefore, you should now have insight that, oh, this can be decomposed into these three pieces, and then whenever you see this something that is proportional to P slash, this renormalizes kinetic term. Why? This thing has P slash in the momentum space, right? So that correction actually adds extra thing to this, right? So now if you compute two-point function, and then the term that is proportional to P slash, therefore, will add a correction to this kinetic term. And then this term makes a contribution to the mass, but there's a little bit more complicated structure, because not only A, but also B, in principle, also contributes to the mass renormalization. But what is at least clear is the term that is proportional to P slash, or fermion, or P square in the case of scalar, for instance. Now you should know that, this is what's doing wave function renormalization or rescaling of bare kinetic term. Okay, you will see more.
There might be the wave function renormalization factor for photon.
Yes, there are.
And
There is.
which looks like a can give.
Vacuum polarization we talked about, but we did not. I mentioned it last time, but we did not discuss in that way before.
But can we distinguish that vacuum polarization gives the renormalized coupling wave function?
Good. So then therefore let me just answer that. So for instance, I go like this before, okay, and then you can have this is Z2, I called it. And then suppose I added a E. This is not totally consistent. That's why I want you to wait until let's just rough. Let me give you a rough idea. Okay. So if I don't include the vertex renormalization, which is not consistent, but suppose I let me do it. Meaning I'm not adding extra. So let me. So suppose you did a vertex renormalization and you had a shift of electric charge. Remember, in addition to the magnetic dipole moment piece, there's also piece that also renormalizes gamma mu piece, which we did not talk about much, but is there. So now you see the effect of this thing is, which is also answering that question about the canonical normalization, canonical commutation relation. So I can now redefine my photon field to be square root of A times A bare. Here I can also redefine my normalized field to be psi bare. So that means that these two terms turns into nice looking expression. The photon connector becomes canonically normalized, and then the electron field is also canonically normalized. This term you see now that should have structure that looks like Z2 square root of A E psi bar will renormalized. So total renormalization of electric charge, therefore, you should take into account wave function renormalization of not only photon but also electron. Okay, and that also answers your question on commutation relation. Anyway, let's move on.
선생님, 그 유닛 파이널터가 이게 P 슬래시 마이너스 MR 플러스 틸다 시그마 수가 그 파이널터인가요? 아니면 그거 분의 1이 파이널터? 이건 말이에요.
Yeah, everything is so basically there's no like as you send capital lambda to infinity, there's nothing blows up. That's why either this way or the other way. Okay. But again, let me again correct it. This may not be absolutely consistent because we have to start including this mass and so on and so forth. But roughly the idea is okay. Let's move on. Was there a question? Okay, so that's big picture quick thing, and then we're gonna continue a little bit. Now I'm gonna switch gear and discuss in the language of renormalized perturbation. So let's now talk about the picture of a renormalized perturbation theory. So here, actually, it is basically this discussion. But anyway, let me do it. Suppose we start with a bare Lagrangian for electron physics now. There's a bare parameter, mass parameter, and then bare electron field. Okay, so I'm just zooming into this part only. I'm not saying that this is my whole theory, but I'm saying let me just focus on here. So using my definition of this thing, relation between bare versus renormalized field, let me rewrite that into this. So that becomes C2, this. And then I'm gonna also write my bare mass parameter in terms of scaling factor and then renormalize the mass. And then, because I also have a field, so this will have secret as well, renormalized. So here let me just write. So I wrote M bare, which is UV sensitive, where MR is UV insensitive. So UV sensitivity is basically scaled out in front of this parameter. Since I'm doing perturbation theory, I can also say that Z2 should be 1 plus small correction. Okay, that small correction, I'm just gonna write it as delta. Whenever I say small correction, everything is modular UV divergences. Okay, the UV divergence will be taken into account. It's also 1 plus small correction. So then you can rewrite this. This is what this is. And this is what we usually treat as a tree-level Lagrangian with a finite mass parameter. Okay? If you have found like talking about bare parameter, which is having a UV sensitivity, just stick to this picture. Okay, this is my classical Lagrangian. Everything is finite. Don't tell me about UV sensitive parameter. This is my answer. Okay? Then if you expand, you have extra piece. So there's a delta 2. This, and then you should get delta n plus delta 2 MR this. So what's the point of this? So I'm gonna say it and listen up carefully. So start from here. Okay, I'm just gonna say it. Start from the classical Lagrangian. Okay, to say everything is finite. And then let's just compute the loop diagram. Okay, for electron cell energy. It has UV divergences. Okay, and then that UV divergence structure can be organized in terms of, now this is a function of P slash and then renormalize the parameter, not the bare parameter. But nevertheless, we can organize in this way. So apparent UV divergences will be stored in A and B. Okay, so if you naively compute it, boom, you get the UV divergence. Now you want to add this extra, what's known as the counter terms. So these are local operators. This is local operator. And then these parameters, delta 2 and delta m, I'm just going to determine their UV sensitivity such that inclusion of this extra correction on top of loop correction will be UV final. Okay, so these are called local counterparts. So for instance, you can call delta 2 to be wave function local counterterm. And then delta m, which is this, you can call it mass counterterm if you want. But that's the same. Okay, so let's see how things work out. So therefore, it's crucial. One loop divergence will be cancelled by extra tree level interaction vertices. You added by hand, those are local counterterms. If you compute the two loop, there will be extra divergence. You have to add extra correction to the counterterm such that again it cancels it. So n loop have a divergence. You have to have n minus 1 loop counterterm to cancel it. Okay, and vice versa. You keep doing this. So anyway, let's see how this thing works out in detail. So don't mix up. Here parameters are finite. Okay, there's no UV sensitive parameter. It's finite. Every well, let me make sure. We're talking about the normalized parameter, which are already finite. And then there's an apparent divergence comes from the loop structure. And then we're going to add extra local counterterm parameters that has UV sensitivity to cancel them. But you know the connection already before I demonstrate that, right? So some combination of renormalized parameter and then UV sensitive counterterm dependence, that was bare parameter, right? And then here too. So there was a UV sensitive piece with a renormalized field that was that is a bare field. Okay. Anyway, so now let's actually see how this thing works. Okay. So now we are talking about renormalization in this renormalized probability sense. So once again, we're going to have one PI. And now, in addition to this loop diagram, so I'm using now this as my Lagrangian. So crucially, one loop over tree level action goes like E2 over 65 squared. But also crucially, the counter term sigma delta 2 and m is also of the order of as it needs to be designed that way, so that if I want to compute things with the precision of the order of this thing, not only I should include the tree level of this thing plus loop correction, but also I have to include tree level diagram of these contributions because that has the same order. Okay, so this therefore I have to include. First of all, let me just put sigma 2 p slash. So that's the one of the contribution comes from this counter term. And then I will have also delta 2 delta m mr. And these all should be in the same order in the loop expansion. Okay. So if you do the resummation, therefore, so let me call this piece to be sigma 2 loop. Okay, so this comes from the literally loop diagram using tree level parameters of the Lagrangian. And then I'm going to call these diagrams to be sigma 2 counter term. Okay, so this is made of tree level diagram, but using a counter term vertices. Okay, they're on the same order, the same order. So if you do the therefore resummation, so now I'm doing the renormalized field theory, right? Because now my field is a renormalized field. So I'm using this Lagrange. Okay. So and then if I compute up to loop order, I should get again resummation. So the entire thing, let me just define to be I sigma 2. Okay, so my I sigma 2 in this renormalized perturbation theory sense includes not only a parent loop diagram but also counterflow contributions. But resummation structure is the same, right? So this is the tree level plus resummation as we talked about. But now let's just actually look into how that looks like. So P slash MR, this thing has not only a the thing from a loop calculation, it also has counterflow contribution. And then the purpose of this counter term, once again, is to take out any UV divergences that you have here. Okay, it's how and why they're introduced. Good. So let's keep moving. Okay, so this thing, the loop diagram structure we talked about can be organized in terms of A B slash, so BP slash, and then sigma 2 tilde. We talked about it, although that was in the context of bare picture. It's the same. The structure is the same. Okay, and then these two things has UV divergence in it. So you see that, oh, if I can pick sigma 2 such that it kills UV divergence come from BP slash, I can remove one of the UV divergences. I can also choose a combination of sigma 2 and sigma n such that it removes extra UV divergences that is hiding in this. Okay, in this sense, you actively subtract the UV divergences by designing your counterflows. Okay, good. So, well, you can rewrite things, everything, but that's redundant expression. Question so far before I moving on. Yes.
I think the psi r and psi r requires coordination. Loop coordination function is defined by p slash minus mr plus tilde sigma 2. Am I right?
You mean after cancellation? Is that what you mean?
Yes. So I think that this is not sigma 2 and sigma 2 tilde.
So that depends on what is known as a subtraction scheme that I'm about to discuss. So, okay, let me say, so far, there's a UV divergence coming from the loop, and then the UV sensitive parameter. Now, the goal of this parameter is to kill, apparent UV divergences. But there's apparent ambiguity. What is ambiguity? Suppose I pick a delta 2 such that it kills UV divergence of B, but I just add 2 on top of that. Nothing changes. At least I can kill UV divergence. At least I can still get the UV finite answer. But in other words, in determining the precise form of a delta 2, okay, at this level, I cannot fix the exact form of delta 2 because on top of a necessary UV divergent piece here, I can add a random finite piece. Still, I can get a finite answer. Likewise, here too. Again, I should have always included a term which successfully cancel out the UV divergent piece, but I can always add extra random piece into that, which does not change, at least, achieving finite UV finite renormalized answer. So this ambiguity about which amount of a finite piece I have included here, that is a question of what's known as subtraction scheme, which I will discuss.
So it is related to the renormalization
Conditions. That's the same thing. Okay.
Professor,
Yes.
the Gaussian scheme depends on a subtraction scheme.
Very good. No, you bet right, as you would expect. Okay, it better not, and it's not. Okay, that's one of the things. Otherwise, you're not going to trust all of you all have different subtraction scheme. Okay, so I already talked about possible ambiguity in terms of finite piece, and then so we have to talk about next topic, which is what's known as subtraction scheme. Or there might be very subtle difference, but I don't care. Renormalization conditions. So this is to fix ambiguity in counterterm problems. Let's see. So I will demonstrate two example main subtraction schemes or main renormalization conditions. Okay. So good. Let's first talk about the first thing. The first scheme is called on-shell scheme. I mean, as you can see, since there are arbitrary amount of ambiguity here, there can be arbitrary amount of scheme you can invent. The only question is, whether you successfully invent something useful or not useful. Okay, so this is presenting two known, either conceptually useful or computationally useful schemes that is known in the literature. So the first thing is on-shell scheme. Let's talk about that. Let's first talk about wholeness. So to do that, okay, so there are two different ways of talking about that, but I'm thinking because I prepared two separate things, but that means I have to introduce extra notations. I'm just worrying you might be confused. Let me try. So therefore, you have to listen up. Suppose A and B include only UV divergences, no finites. Okay, so in other words, this thing looks like E squared over 16 pi squared lambda squared, something like that. But say I don't add the 4 pi. Okay, so suppose we organize it such that this A and B have only UV divergences with no additive finites with it. Okay, so that's all included in sigma filter. Okay, then let's organize the way that so then delta 2 at least must include minus A so that it kills the UV divergence, right? And then possible finites. Let me call that to be finite sub 2. That's crazy notation. I understand that, but I did not come up with a better notation. So what about this thing? So then delta 2 minus delta m as a whole at least must include A over MR. So this is designed so that it compensates UV divergence of this thing. But again, there is ambiguity. Finite. So let me call that finite sub n. Okay. So at a priori, you wouldn't know how much finite bits you have to add or not. But once again, it is a subtraction scheme will tell you exactly how much you are going to add it. Okay. So this is I'm setting up notation so that I can talk about it. So good. So then I'm going to rewrite this thing as follows. Therefore, so now P slash MR, so far so good. And then this thing cancels. And then I will have a sigma, oh, where is my, okay, sigma 2 tilde. Oh, B. Thanks. B. Okay, very good. So then sigma 2 tilde from this bit, which is UV finite. And then I will have a finite 2 minus finite m, right? Ambiguity. So let me just call this entire thing to be the sigma r. So I told you, I might have to introduce extra notation, but here we go. Okay, at least I told you exactly what I mean by this notation. Okay, with that notation, now let's define Paul mass. Sigma of psi r bar now can be written as this. And then this include that ambiguity of finiteness. Okay. Now pole mass obviously is that there's a pole. So pole mass is defined by pole mass location is m sub p, to say pole or physical. It's either pole or physical. Is literally the location of the pole of this problem here. So pole is when p stage evaluated at NP should be 0. So this defines that NP must be a simple pole of this function. And as I said, either pole mass or physical, so it is actually physical, which means if there's actually electron, and then it's actually made a long distance propagation, okay. Ultimately, it does that. It does so because, broadly speaking, it has p slash minus np propagation. So remember, long propagation comes from hitting exactly the pole location of the propagator. If that doesn't make sense to you, let me say that again. So suppose I want to look at the electron field at x and then y. And then I want to see when this thing is non-zero, even though I take very large. Okay? So then this thing is what? A to the ip dot x minus y, and then p slash minus mp. So if you take very large separation in the space and time, then this is a wild oscillation. Everything cancels out except you hit the polar, singularity. So long propagation comes from the region in the momentum space where you hit the singularity. So if I actually prepare the electron beam and shoot to the moon, I don't know if somebody's there, observe that. That means, because electron hit the pole. I don't know what that means. You know what I mean, right? So that happened. So this thing is a physical, okay? So this pole is a unique and invariant definition, and this is a physical mass. So if you want to talk about, what is electron mass, which is a 0.5 MeV, you're talking about this physical pole mass. All right? Good. Yes.
I think the sigma r also includes the imaginary part.
Not at this level, no. You're right in general, yes. So good. So he said that this can, in principle, can have an imaginary part in it. In principle, it can have imaginary part in it, yes. But if I take a free electron, but somehow include this loop fraction, okay? Or if you want, if I include this loop fraction, making a photon mass being larger than half of electron mass, then this thing does not develop actually an imaginary part, and it's completely real. Okay, I have not gone into that discussion yet. So let me just say, this can, in principle, have an imaginary part, and I'm gonna say a mysterious statement to you. And that imaginary part, according to the optical theorem, is related to the decay process of electron. Here I said I'm gonna assume electron is free and stable by saying that there's no state into which electron can decay. That's why I said the photon has a mass greater than m/2. So then this is purely real, and I don't have to worry about that. Okay, otherwise, you're right. Then there's no simple pole. In that case, okay, 3 minutes, forget it. Okay. In that case, instead of being a pole, isolated pole, it is a beginning of a branch count. Okay, but forget those 3 minutes. Another question. Okay, let's keep moving. Good. So then, pole mass should be in such a way that, so the part of the definition of pole mass should be in such a way that this complicated looking expression should be near. So if I go very close to the pole mass, so there's a complex plane, and then I go to the very close to the pole mass, this thing should look like all types of prescription I. Okay, so this is canonical looking propagator. But now instead of barometer, in terms of pole mass. So this thing has two conditions. So this equation actually encodes two non-trivial conditions. This thing consists of the two conditions. So I would say that on one condition. So one is about this being a pole mass, and second being this comes with a residue being equal to 1. Okay, this has two conditions. Let me make it more precise from now. So to do that, let's write this. So P slash, this is the denominator plus M renormalized. Okay, so then this can be very close to, again, the pole mass. I'm just going to expand this expression. That will be MR sigma R evaluated at this, and then I'm going to tail expand. So which will be first derivative is P slash sigma R evaluated at this is equal to MP. But this is, first non-trivial order in the tail expansion. And then we can have a higher order. But guess what? This combination right here is exactly the definition of pole mass, according to this definition. Okay, so if you hit the pole, this combination is exactly the definition of pole mass. So this can be rewritten very close to pole mass as M pole higher order. So that means I can also rewrite as 1 plus okay. So you immediately see that one of the condition, like in order to satisfy this, is to say that this must be 0. Because this, if you take 1 over that expression, if this is non-trivial, then obviously you will like have 1 there, right? Reciprocal of this, in order to match to that, it should be 0.
Sigma R is at least P squared.
At least P squared.
So the P linear term have to be equal to 0.
Oh, that's what you meant. Sure. Yes. Yes. Or okay, actually, it's a slightly a little well. If you have a higher order than P slash, then whatever it is, if you take the derivative and you validate MP, it should be 0. If that is the condition. This is so far I'm phrasing not a perturbative statement. I'm just phrasing actually just the exact statement. Right? If somebody handed me this with the ultimate power of computing this to the 100 loops, this should be true.
On the pole mass onshore scheme,
Yes.
if we go this condition, the first derivative term will be strictly 0.
Yes.
Even if we calculate the order.
Yes. Yes. Good. So now actually, because this is one condition of on shell, I'm gonna state on the second condition of 2 conditions. Okay, so that's one of the conditions. Second condition, which is part of this on shell scheme. So this is again, this is true in any scheme. Okay, this is true in any scheme. This is just definition of a pole mass. Okay. Now the second condition, part of the on shell scheme, is that in on shell, we normalize the mass is identified with the pole mass. So that's the second condition that I'm imposing. So what it means is that this immediately gives you the condition that sigma r evaluated at pole mass should be 0. This is your second condition. Effectively. In terms of sigma r, you have these two conditions to satisfy. Now let's go back here and ask ourselves. This was sigma r. You had a two ambiguity, right? You need to know you have to have two conditions to fix these two ambiguities. And then I'm giving you two exact conditions so that if you successfully incorporate these two conditions, then this will be uniquely determined. Okay? Good. Good. So let me, okay, so conceptual what's happening. Just computing, organizing things, okay, I cannot fix these two. In order to fix, therefore, you have a unique expression now. Somehow you have to impose conditions that allow you to fix these two finite ambiguities. And in one of the scheme that allow you to fix these two is known as on-shell scheme. Okay, on-shell scheme is in terms of pole mass. It is a phrase in terms of pole mass. The first part, I just defined you what is a pole mass. It's a physical and it should not depend on the scheme. Okay, it's just definition. However, as a one, in on-shell scheme, you require that A, reversing order, the normalized mass parameter should be already identified with a physical mass value. This is not a parameter, this is actually a number, right? And this gives you one of the conditions to fix one of these two ambiguities, because I have two unknowns, I have one conditions. Second condition is that if you hit the pole, then I want to see the propagator, exact propagator, not including loop correctness, but that should have a residue 1 as you hit the pole. Okay? So this condition, which I analyzed here, because I just took the general denominator, I just analyzed near the pole mass region. You can just expand it out, distribute overall structure. In order to achieve one residue, then you know that the condition is that this should be satisfied. So this makes the second condition of reverse order. There are two conditions, therefore you can fix those ambiguities. Questions? Okay. Okay, so let's continue. So you should be able to re-express these two conditions in terms of, not in terms of sigma r, but in terms of original sigma. Oh, original sigma. I erased it. Let me just mention it. Remember, if I just compute the psi r, okay, what you get is I over, remember, since I'm in the renormalized part of this theory, I start with this parameter. And then you get sigma 2 from the loop, and then sigma 2 from the column. Right? So now what I'm saying is that I told you the condition in terms of sigma r, this physical conditions, but you can also derive condition in terms of this. And then if I remind you, this thing has sigma delta 2p slash minus delta 2 plus delta m and mod. So since this should be already pole mass, right? Then this entire thing evaluated at the pole should be 0. So that's one condition. Okay, so that's one of the conditions. And then by expanding this piece close to the M pole, so you have a MP slash, and there's also P slash dependence. By expanding these two combinations near the M pole, you can derive what could possibly contribute to wave function renormalization, like this. And then by setting that to be 0, you get the following two conditions. You should be able to check explicitly. So the second condition actually, so this condition, let me, sorry for reversing order, but this condition should be expressed in terms of delta M parameter should be 1 over MP sigma 2 loop, where P slash is evaluated at this point. So let's first appreciate what this equation actually means. Remember, if I naively compute the loop diagram, it will have UV divergence. And then I design this one of the parameters to kill one of those divergences. This will have a UV divergence according to this equality. Not only that, this, if I just compute this thing, could have a finite disk in it. And this, therefore, by equality, it tells me what amount of a finite disk this delta M must include in it. Okay? I organize it anyway. So then the second condition, this condition, the zero, no non-trivial wave function. But that condition, again, exactly the same exercise. Should give you sigma to loop, slash, evaluate that. And likewise too. So if you take the derivative, remember, so this thing had a plus EP slash. So if you take, and then finite this. So if you take the derivative, this divergence drops out, right? So this, therefore, sense is divergence hiding in the V. But on top of that, if you just evaluate this thing, this may make a finite contribution to that. And it tells you how much finite this delta 2 must include. Okay? This is how this ambiguity is lifted by putting concrete renormalization conditions or subtraction scheme. Okay? So that's the on-shell scheme. I'm going to talk about the second scheme, but are there any questions? Okay. So hopefully you appreciate, the entire discussion I'm giving you today. I have not completed any single loop diagram. There's a lot of a subtlety concept, okay, and you really have to get it. And then computation is meaning. Otherwise, you know how to waste your time computing things. We don't know what to do. Okay, the second subtraction scheme is called the minimal subtraction. It's often written as MS to say minimal subtraction. So here the point is that delta 2, delta n, or in general, all the counter terms subtract, or remove, and so on, whichever one you're going to use. Only UV is, and in this case, schema 2. Okay, meaning no any finiteness in output. Okay, so that's the definition of minimal subtraction. So you literally kill, you do the minimal job. Okay, I'm not gonna do extra job. I'm just only gonna kill the divergence, but don't give me any finiteness. Okay, so probably it is better to actually see the explicit expression to see how this works. We must be clear. Whatever divergence you see here, just now don't drop all the finite pieces. That's what it means. So there is also a constant version of this. It's called modified minimal subtraction. And we can guess the notation for this, acronym for this. What? MMS. Actually not, so you could call the MMS bar. Okay, that was a good guess by the way. So the idea is, so this is used only if you compute things in the beam range. meaning if you regularize UV divergence using beam reg, then this is meaningful. So just to illustrate the point, for instance, when we computed the vacuum polarization diagram of this, so this thing had a piece that looks like this is just to illustrate. The computation is not the key for this. So then this thing had a 2 over epsilon, and then log log of 4 pi e to the minus gamma e u squared delta divided by delta plus 4 epsilon. Okay, so we computed this and you have seen this. And then previously, I defined this combination because they almost always appears together, this particular combination. Whenever you compute things in the beam reg, they appear ubiquitous together. So we just define these to be u tilde squared, okay, at the same time. Now, if you use MS scheme, meaning minimal subtraction, not the minimal MS bar scheme, then you will add an extra contribution from a, in this case, let me call delta A. Suppose you added a contribution from a local counterpart. So in addition to this, which stand for only loop, you add extra sheets like this, which multiply the same universal spectrum. Okay, so if it were MS scheme, then you design delta such that it only removes this 2 over epsilon piece. Okay, so it's literally remove only divergences, nothing else. But if you have done MS bar scheme, then to that end, let me rewrite this piece here. So this piece here can be rewritten as the extra 4 pi e to the minus this, and then log of u squared delta. Okay, so since in beam reg, this junk right here is like ubiquitous. Okay, so you can just set a clean designated goal to swallow this thing as well. So in addition to 1 over epsilon fold, which is UV divergence, you always add this thing to the counterpart such that you always get rid of this piece. That thing is called MS bar. Okay, so it's almost MS, but just get rid of universal numerator factor that you always have in beam reg. Okay. Okay, so any questions so far? So I might take like 5 more minutes. That's okay. To now illustrate the point using actual expressions. So far, everything is, abstract notation. So I'm just gonna illustrate that. I'm not gonna compute it, but I'm just gonna, use the result to tell you how things work. Okay. So remember, own shell scheme. You set renormalized mass already is equal to pole mass, and then the second condition was residue of the pole and P should be 1. Okay, so that was a condition. So and then minimal scheme, you only get rid of divergences. Okay, so if you have actually computed this diagram, I dropped that 3 times. So if you actually computed this thing, which is this, so we can give a momentum P, K, P minus K, and you can compute it. So you can compute it in 2 different ways. This is again logarithmically divergent. You can regulate it in 2 different ways. So if you look at the book, there's some procedure, but there are omitting procedures which you will be asked to do it. So in polygonal regularization, if you do the computation, so this sigma 2 loop is given by alpha over pi. So that's roughly is E squared over 16 pi squared, as you expect. Remember, alpha is E squared over 4 pi. Okay, so fine structure constant is defined to be that particular combination. And then there's M. So let me put R actually, because we are doing in computation in the normalized for division theory sense. Then over 4 E slash same thing, and then finite piece. So first note that this goes like again E squared over 16 pi squared up to numerical factor, and then A plus B E slash plus finite piece, as we argued. Okay, even before computing anything, we argue that it should have that form. In fact, it is, right? So one is proportional to this. This is A. And then it has UV divergence in it. And then P slash, this is P slash, it's proportional to that. It has a UV divergence in it. And then there's a finite piece, as we expect. Okay? And you should know by now that, okay, yes, this guy will do the wave function renormalization. And then likely this will shift the mass parameter. But there's some complication because this also contributes to that, and so on and so forth. We talked about it. Okay, let's look at the calculation done in the DMRAC. So if you have done the calculation in DMRAC, you should get sigma 2 L slash, which is alpha over pi. Once again, E squared of 6 pi squared, P slash 4M. 2 epsilon plus finite piece. Same, okay? So there's A plus BT slash, which is UV divergent, finite piece. Okay? So let's do the let's just do the minimal subtraction in DMRAC. Okay? Just to show how things work. Okay, so let's do the DMRAC. Sorry, let's renormalize this thing using DMRAC. So how do we do it? Well, remember, if we actually computed things, including a counter term contribution, then this, which is this, is now sigma 2L from the loop. And then we call delta P or delta 2P slash minus delta 2 delta M MR. Right? So if I were to do MS bar, oh, do I want to do MS bar? Oh no, let me just do MS. Okay, then otherwise I have to start looking at what's there. Okay? Although MS bar can be done trivially too. So now delta 2 have to kill this guy, UV divergence. So delta 2 is fixed to be minus of that thing, which is minus alpha over 2 pi 1 over epsilon. Okay, happy? And then delta 2 plus delta M should be, since there's an overall minus already, should be the same as the second term, which is minus 2 alpha over pi 1 over epsilon. Okay, so you can trivially determine delta M by subtracting delta 2. Okay, and you should be able to do the same thing for MS bar or on shell scheme. Okay, the game is the same. Conceptually, it's exactly the same, just different mathematics. Okay, any questions? Good. So I think we covered basically more, other than actually getting these expressions, which will be part of the homework, last homework I will post today. We basically covered electron self-energy renormalization, including wave function and the mass renormalization. Next time, we're gonna just combine everything together to see how things work out in a single platform. Okay, in terms of a renormalized for the region. That will be fun.